Beethoven music going in the background. And it's winter break, and I just had this problem I've been thinking about in my mind about the toilet paper problem or lab that I had you guys do. So let's take a look at that. And I'm trying this new app. I'm trying to draw all of this with my fingers, so don't judge me. Alright, so toilet paper lab. Right? And one of the things I asked you guys to do was to try and figure out if you have a toilet paper roll, like so, what would its moment of inertia be, right? And we tried to measure that through the lab, but I want you to think about it theoretically. Theoretically, more or less, you can kind of think of it as a cylinder with its mass evenly distributed throughout itself. I mean, I guess you can argue there's the cardboard in the middle, but whatever. We're going to ignore that. Just as an estimate, right? And so it's like a cylinder with a hole in the middle. And so you might be inclined to think, well, there's an outer radius. We'll call this RO. And an inner radius. We'll call that RI. And you might be inclined to think, well, it's just, the moment of inertia for a full cylinder, right, minus the moment of inertia of what's missing on the inside. Well, the problem with that is, how do you calculate the moment of inertia for a full cylinder? I think it ends up being 1/2. Oh, goodness, that's so bad. No, go back. Let's see. Nope. Seriously, where's the eraser? Okay, that totally didn't work. Okay, so say the whole toilet paper has a mass M, and so that mass is distributed over the toilet paper, and for a cylinder, your moment of inertia is 1/2 mr squared, right? And so the question is, this mass, it's supposed to be the mass of the whole cylinder. So if you try and use the mass of the toilet paper to represent this guy, that's not going to work, because that mass is not distributed through a full solid cylinder. And so when you subtract away this guy, what is the mass of this guy, right? Because that's not the mass of the toilet paper. It is whatever you would subtract away from the center, such that the toilet paper actually has a mass M. And so you can't just take this subtraction method. This would only work if you had a full cylinder. Let's say you have one like this. Okay, let's say this guy's over here. You have a cylinder. This is a mass M, right? And you also had this guy. And in addition to that mass, you had, say, like a second one in there. And this also had mass M. Then you could, subtract. It wouldn't. This wouldn't make any sense anyway. Only that, you'd have some moment of inertia of the whole thing that is the combination of both. And so if you subtract away this guy, it doesn't matter, because you still have a solid cylinder on the other one. But that's not what we want. What we want is a hole, right? We want a hole. There's a hole here. And so how do we do that? So this is where we actually have to use some calculus. You have, let's see. Okay, so you calculate moment of inertia, that's I. And we said before, you integrate all the little pieces based on the square of their distance from whatever your pivot, right? So the problem is you need a way to represent this mass based on a distance, right? So one trick to do that is you chop up, in this case, we're going to chop up our circle. So you have a circle here, and you have a circle here, right? And what we're going to do is we're going to make these infinitesimally small rings, right? And this has a depth to it, but that doesn't matter for the moment, because that's not what actually influences the moment of inertia. It's the radius, right? And so this ring has some radius. I'm going to use little r, okay, distance from the center, the pivot, right? And this has some thickness to it, some infinitesimally small thickness, and we're going to use that infinitely small ring to represent a piece of our mass, right? And so how do we relate how thick that is to how much mass there actually is? Well, if it is uniformly distributed, if the mass is uniformly distributed, then whatever the ratio, oh goodness, this thing again. Okay. Whatever the ratio of the mass of the full object, right, to divide it over all the volume, and to represent the volume in this case, we're going to do essentially the area, right? So you got the area of the big circle minus the area of the inner circle. So we could actually include whatever the width of the toilet paper is too. But again, that really doesn't matter. Well, for completeness, let's go ahead and do that. So okay, so let's say this has a width to it, right? And so the volume is that much. So if the mass is divided over all that volume, then that is essentially its density, right? And so if it's uniformly distributed, the density should be the same everywhere, which means that this ratio should be the same as the ratio of the infinitesimally small mass over the volume of that infinitesimally small mass. Right, and so the trick to figuring out the volume of that is, and this is kind of a shortcut, but it is essentially 2 pi r dr. And then of course there's the width, but the area of that ring, the area of the area of that ring. Let me see if I can highlight it here. Right, the area of this. It has a thickness, we call it dm, meaning it's a differential piece of mass, but it is also has a differential thickness, dr, right? And so that's where that's coming from. And so this all together is like an area, and then this whole thing is like a volume. Right, so same thing, it is a density. So the density of the whole should match the density of the piece, right? And so when you look at, let's see, when you look at this guy, right, this is essentially adding up the moments of inertia of all those little pieces, right? And so what we're doing is we're trying to convert this into something that is spatially meaningful. Okay, so that's what we're going to do next. So I'm going to take this guy. No, I can't take that guy. Okay. Nope. All right. I'll just make a new one. Okay, so we said, I'm going to write it again. m. And you can see from the other one that the, oops, I don't want the color. Okay, we can see from the other one that the width cancels out, right? Because you multiply the volume or whatever, the area by the width on the one side. Right, there's a width on this side, and then there's also a width on this side. So it cancels out anyway, doesn't matter. Okay, and again, the reason why it's r naught squared, or our outer squared minus our inner squared, and not the square of this, right? That is incorrect. You wouldn't. It is each of the areas subtracting, so don't want that, right? So get rid of this guy. Okay, so from here, what we're trying to do is we're going to solve for dm in terms of dr, because that's ultimately what we want. We want to try and get our differential piece, our differential mass is a spatial element, a differential radius. So let's just cancel stuff out. Pi's cancel. And that's it. Okay, so we have mass, 2 mass times r, right, over r outer squared minus r inner squared, and that is, oops, dr is equal to dm. Okay. This, again, I'm trying to draw with my fingers, so don't judge me. All right, this is perfect. So what we can do is we can take this and we can substitute it. We can substitute it back into the what was it? The moment of inertia integral, right? And again, you know, sometimes these integrals look kind of scary, but don't get intimidated by them. In the end, they're essentially antiderivatives, right? So let's go ahead and substitute that back in. In the others, we said it was 2. What was it? Yeah, 2r m big M over r outer squared minus r inner squared dr equals to dm. Okay, so we're going to substitute all that in. Now notice that these, those are all constants. So when we substitute them in for dm, they can all actually go outside the integral. Just like when you're taking derivatives, constants can come outside of the derivative. So that's what we're going to do. We will have 2m over r naught squared minus r inner squared. Integral, now we have r to the third power dr. Okay, so now this is really nice, because if you look at this guy, you are trying to integrate where r is a variable, but you're trying to integrate in terms of mass. And that's really weird, because there is an implicit kind of relationship there. And it makes it a lot easier if we have, instead of little slices of mass, we have little slices of radius. And then we integrate along that radius, right? And so this is the part where you actually do any sort of actual calculation, calculus-wise, right? And so you're looking for an antiderivative of r to the third power. What, the derivative of what gives you r to the third? That's r to the fourth over 4. So you can actually do this, and let's see, I always run out of space. Okay, so I'm going to draw a little smaller here, but, and if we think about what we're integrating, we are integrating, in other words, when you take an integral, you are adding up a bunch of stuff. And so you have to tell the integral where to start and where to end. And so we're starting from the inside, and we're going all the way to the outside. And I know I didn't write this in the other integrals, but I guess for completeness, you really should, since these are not indefinite integrals. They have boundaries that are defined. But for the sake of this, it's just imagine putting these limits back in. Anyway, so to translate this, we have again the stuff on the outside, or the constants. Okay. And now we have r to the fourth over 4. And the notation here I'm going to put, this is bar, is I haven't substituted in the limits yet. But I'll show you how to do that. I just kind of ran out of space. So let's go ahead and do that next. Okay, so you have constants. Okay. And this thing basically means, oh goodness, whatever. You're going from R inner to R outer. And so it translates into something like this. This guy again. Okay. And you essentially have R outer to the fourth over 4. It's as if you substitute this in for the radius, and then you're subtracting away when you put the other one in, R inner to the fourth. Right. That's all you do. You're taking the difference between the limits. Okay. Okay. So we can totally start to simplify now. Those kind of turns into 2's. We can actually group the top together. And so, if you look, this actually simplifies to m over 2, okay, r outer to the fourth minus r inner to the fourth, divided by r outer squared minus r inner squared. Now, if you're tempted to just cancel out the 4 and the 2, you're doing it wrong. You can't do that because they are, math. So the trick here is we're going to expand this because this is a difference of, this is a difference of perfect squares. Okay, that lives there now. So let's see. So difference of perfect squares, right? So the top part, I'm just going to write the top part, is r outer squared minus r inner squared times r outer squared plus r inner squared. Right? That's the top part. Okay, totally running out of space. So after we do split them up, the perfect squares, right? R outer squared minus r inner squared. And then you add them. Now we can see that those cancel out. So our final result, which is actually really interesting, remember this is supposed to be the moment of inertia of the whole thing, right? The moment of inertia of your toilet paper situation. Actually, I don't like that. Let me write it differently. Oops. Just to draw the parallel to how a solid cylinder looks. It's 1/2 m r outer squared plus r inner squared, which is really interesting. You're adding the inner radius, which actually makes a lot of sense because if you compare, let's slide this up. Slide that up. Slide that up. Okay. If you compare the moment of inertia of a ring, right? A ring where all the mass. Okay. New slide. Okay. So here it is, 1/2 m r outer squared plus r inner squared. And this was for something that looked like this, right? Your donut. Okay, and if you compare it to when you have a ring, or the hoop, right? The idea is the thickness of the hoop is irrelevant compared to the radius of the hoop, and so all the mass is pushed to the outside, and that moment of inertia is 1/2 m, or no, what am I doing? It's not 1/2. It is just straight up mr squared. Right. So think about this one. What happens if the inner radius is equal to the outer radius? That would imply you have essentially the hoop. And if you look at that equation, you'll have our outer squared plus our inner squared, and then that's 2 times our outer squared, which cancels out with that, and then you essentially turn it into this, right? And so that makes sense. Think of the other extreme. What if your inner radius is 0? You have the whole not exist. It closes all the way. Then this goes away, and you have essentially 1/2 mr outer squared, which is what it is for a solid cylinder. So actually, if you think about what this is doing, what it's doing is it's recognizing the fact that as you push this hole out, the mistake is to think that the mass is disappearing, but the mass is not disappearing. The mass is being pushed out. And so, like we said before, the more the mass is pushed away from the pivot, the more the moment of inertia actually is. So so you think all the way back, the mistake of thinking of the hole as a cutout is that you're thinking you're cutting out the mass, but you're not. It's like you're compacting that mass into a smaller and smaller area that is on the outside of the ring. So, main point is that is the moment of inertia using of your toilet paper. But I want you guys to think about how I went about solving this, using the integral, using that substitution. I think it's really important recognizing this step again where I took, and again, this mainly works for uniform distributed mass, but it doesn't really have to be. There is some, in this case, there's some density which tells you your mass per volume, right? And in this case, when you talk about uniform density, that just means this is constant for uniform distribution. Right? And so you have a solid cylinder, or however you want to determine your volume, right? And you just substitute it in. And it's just recognizing that your density, if it is the same everywhere, is then therefore going to relate to, going to have that same ratio. Anyway, I hope you enjoyed this video. I hope it wasn't too long, and I hope you learned something.